Assalamu alaikum. I'm Dr. Hassan, Assistant Professor of Medical Metabolism and Immunology. The medical term was a graduate of medicine school, it's not pharmacy school. I'm a graduate with master's degree and MD degree from Faculty of Medicine, Cairo University. I'm honored to teach my students, my great students, at the Pharmacy College, Salt University. We are going to talk today about antimicrobial resistance. The contents of our lecture today is going to cover, or at least scratch on the surface of this item: antimicrobial resistance crisis, the etiology of this crisis, the origin and types of antimicrobial resistance, the difference between the interesting and acquired antimicrobial resistance, the mechanisms, and how to fight such a big crisis. The motivation of this study, or every study done, especially in this antimicrobial resistance, is because it became the most important problem in the infectious diseases. Nowadays, when even in our patients, when it comes an infectious disease that's on a large scale, that the problem is very severe now about how to deal with it without emerging the resistance against it. We all hear now about the coronavirus, the similar virus to SARS, the swine flu, and the big issue is how to deal with it and treat it. A lot of studies faced this problem. The ICU unit is one of the most problematic departments in our hospitals all over the world. The National Nosocomial Infection Surveillance covered almost all the infections, especially the MRSA and the vancomycin-resistant Enterococcus. As we can see from these graphs, that it's rising. It's rising. The methicillin-resistant staph became from 1995 to became from 30% to become near to 70% resistance. As well as the vancomycin-resistant Enterococcus, it became from 15, almost the resistant strains from 15% to almost 35% in 2004, and still rising. This is about the gram-positive. The gram-negative strains still rising antibiotic resistance. The generations of Klebsiella, the third generation cephalosporins was effective completely 2 decades ago in treatment of Klebsiella pneumoniae. Right now, it's almost 30% of them are not treated by this drug. As well as fluoroquinolones, they are still rising antimicrobial resistance in the Pseudomonas aeruginosa, which is a big issue in our hospitals right now. Emerging new antibiotic resistance mechanisms are rising as well. Mechanisms we never heard about before, now rising. Especially in the Enterobacteriaceae group, which is a very big group and affecting us all over the world, all over the departments, especially 2 in the ICU units. The carbamazepine producing Enterobacteriaceae is rising. In 2003, it was negligible amount. Now it's rising to almost 70 and more than 70%. What about here in Saudi Arabia? Actually, there's a limited number of studies that issuing the progress of the diseases and resistance all over the years. MRSA strain was tackled by our colleague and very best friend of mine, Dr. Manal Baddour, and our previous or ex-dean, Dr. Amal Fatani, if you know her. Of course you know her. She's one of the most distinguished professors. They were doing this research in 2006 about MRSA strains from 6 different hospitals. Unfortunately, it was sensitive to vancomycin, quinapristine, and dalfopristin, which is streptogramins, and linezolides, which are the last resort now for our treatment to MRSA. And one of my studies and my colleagues in our pharmacy school here in Saudi Arabia in 2012, we issued the Acinetobacter pulmonale organism. It was found that 23% of our strains were resistant to all used antibiotics. All the used antibiotics, 23% of our strains were resistant to them, which is very big percentage. Actually, we tried tigecycline and moxifloxacin. Tigecycline give a very good results with it. Why resistance develops? Why? Is it really the mistake of the bacteria itself? No, of course not. It's our mistake. We misuse antibiotics. We give it wrongly. We outdate and take outdated and weakened antibiotics stored wrongly. They are weakened by several factors actually. They are expired and we still use them. Inappropriate conditions. We give antibiotics to common cold, viral infections. Is it gonna work? It's not gonna work. Actually, it will just flourish the resistance strains. Another inappropriate condition is giving it inadequately. Sometimes we have urinary tract infection. Urinary tract infection, usually we have to use antibiotic that is concentrated in the urine to be effective in such a state, you know. So we give it, and it's not concentrated in just like nitrofurantoin and other drugs that are concentrated in the urine. If it's not concentrated in the urine, it wouldn't work. So just we are selecting the resistant strains by giving it inappropriately. Failing to complete the prescribed regimens. So I'm well now, so I will not continue taking this drug. That's not right. Leftovers. So I have one kid that have tonsillitis and I give it to my other kid, the same prescription. So if he has no tonsillitis, if this leftovers is not enough, so I'm harming my child. Latest wonder drug. This is completely wrong of our clinicians. They just hear about a new drug and so they are prescribing them for the sake of the pharmacy companies. I don't know why, but so if it's a very good drug, why use it? Why waste it? Why waste it? If you use it that much, it will be wasted. It will develop resistance in no time. Okay, and using antibiotics in animal feeding. Actually, animal feeding is a big problem. Many farms use it to improve their livestock, not to treat, no, just to improve their livestock. So it's not mandatory to give them. Many studies were done about that subject, and actually in USA, as we see, this is a study done for fluoroquinolones as well, for resistance of Campylobacter jejuni. As we see, ouch. Fluoroquinolones in 1986 were never resistant. There is no resistance at all. By the year of 1994, and then after we started using it in poultry, in chicken and ducks and so on, it became raisingly resistant. They stopped it at about 2005. It improved a little bit in 2006, but still it's rising due to other factors. I meant just to say, if we have this collaborative work, we could decrease it a lot. These are minor factors that affect development of resistance. Traveling from one place or another, you know, here in Hajj and Umrah, especially in Ramadan, a lot of travelers come here to Saudi Arabia, coming with new strains to us. You know, they are not new to them, but they are new to us. So we are susceptible to them, you know. So poor sanitation works with that. Food, especially outbreaks in food. We heard about the E. coli 0157. Just I think a few months ago, it developed an outbreak in food especially in British and Spanish in USA, in Europe. It causes urinary tract, actually hemorrhagic diarrhea and severe renal failure from this infection. It comes from food, so it's an emerging infection, and it's resistant to a lot of antibiotics. Emerging and re-emerging infections. Emerging infections, as we hear every day. Swine flu, corona, SARS, and every day we hear about new disease. Re-emerging, just like TB, you heard about rising of TB incidence again. Actually, by the 80s, TB decreased a lot. Nowadays, it's a very resistant disease, multi-drug resistant. Hospitals, it is the reservoir of our infections. The reservoir of the resistant bacteria. Resistant bacteria come together and they infect each other with resistance, as we will see, inshallah. So, using these, I don't know. Sorry. So, we select the resistant strains doing that, using wrong antibiotics, using the prescription wrongly, using these wrong antibiotics in virus infection. We just select them, what we call a selection pressure. What happens is, when the bacteria are here in my throat, and it's a resistant strain, and it's one resistant strain, and surrounded by these just commensals. What happens is they are competing with these resistant strains for nutrition receptors, so the resistant strain cannot flourish, cannot overcome these other normal susceptible bacteria. What happens if I give strong antibiotic unduly? What happens is that I kill all the sensitive and susceptible organisms, and who flourish and find a good media for much food and much receptors. Actually, the resistant strain will find that, and it will flourish, what we call, as I say, selection pressure. That's what happened. Resistant strains, just one among susceptible. As it remains like that, it never causes a problem. The same you will see in these plates, even in our plate in our lab. If we just give a strong antibiotic and there is two resistant strain among all susceptibles, the resistant strains will flourish and increase as we kill the susceptible ones. If I interrupted my course of antibiotics, the resistant strain will flourish and become predominant. In every bacterial community, this curve is preserved almost all the time. There is highly sensitive organisms, intermediate organisms, and highly resistant. As we give the antibiotic, they decrease by time. If I don't complete the whole course prescribed, what happens is I kill the highly sensitive, the intermediate resistant, and I preserve the highly resistant, and they prevail and they become very large in number. Clinicians call this organism to be resistant when the MIC, or the minimum inhibitory concentration of the drug of a particular strain exceeds its capable being achieved with safety in vivo. Minimum inhibitory concentration, when the serum level of the antibiotic becomes toxic in our blood, that's when the clinician calls this organism is resistant to this antibiotic. What about the cross-resistance? Cross-resistance usually happens between closely related antibiotics. When an organism is resistant to penicillin, it usually is resistant to cephalosporins and other beta-lactam groups. When I call it multi-drug resistant, what I mean is that it is resistant to multiple drugs that has no relation to each other. So, what is the types of this antimicrobial resistance? We have two important types: the intrinsic and the acquired resistance. What we call intrinsic, inherent, or natural resistance. That happens when the organism is naturally produced in nature like that. It's resistant to this organism. Acquired resistance, it means that it became resistant. Naturally, it's sensitive to these antibiotics and became resistant by time. The intrinsic inherent natural resistance, usually we have these number of examples. Enterococcus resistance to cephalosporins because it lacks the target enzyme that cephalosporins work on. Mycoplasma lacks its cell wall. All beta-lactams work on the cell wall, so lacking the cell wall is naturally a resistant factor, and it's created like that in nature. Streptomycetes is one of the most important producing bacteria to antimicrobials. You know, streptomycin, erythromycin, rifampicin, tetracycline. These all famous antibiotics are produced from streptomycetes. If they are not resistant to their own antibiotics, they will be killed. So they are resistant to their own produced antibiotics. Gram-negatives are resistant to the antimicrobials that are very large in molecular size. So the most important ones, naphthalene, which is most of them doesn't, it simply doesn't enter into the pores. The origin of resistance, the acquired resistance, the origin is through two factors: either mutation, that we call chromosomal factor, or vertical evolution, or exchange of genes, or extrachromosomal or horizontal evolution. Let's remember together how does the antibiotic work. It works either on the cell wall, inhibition of the cell wall synthesis, just like penicillins and cephalosporins and other beta-lactams, acetylcysteine, vancomycin, or either it works on the plasma membrane, just like polymyxin, or it works on the nucleic acids, just like rifampicin, it works on the RNA, or quinolones, which works on the DNA, prevention of replication, or it works on the DNA protein synthesis. Either it works on the two subunits of ribosomes, 30 or 50 S subunits. Inhibition of protein synthesis, just like chloramphenicol and erythromycin, it works on the 50S subunit, while the tetracyclines and streptomycins, it works on the 30S. Finally, it works also on the metabolism inside the cell, especially in the folic acid production, the sulfonamides and trimethoprim, it works on the folic acid production. Mutation or chromosomal, or as we call it, vertical evolution, usually happens spontaneous by time, just by time. Gene sequence change. This mutation may change the target, as penicillin binding proteins in the case of Staph aureus. Streptomycin and tetracycline resistance would alter just the target organ or the target receptor on 30S. Erythromycin resistance alters the 50S subunit, while polymyxin resistance due to cell membrane charge alteration. Or it's due to a change in the gene, exchange of genes. That's what I call infection. Usually bacteria infect other bacteria by resistance. What happens is, the bacteria has a plasmid that can move from one bacteria to another, and it carries resistance, or transposable genetic elements that can move from one bacteria to another. What happens? Usually, these plasmids and transposable genetic elements just move. Actually, the transposable genetic elements we call usually the jumping genes. It usually uses plasmids, phages, even chromosomes to transfer from one bacteria to another, as well as the plasmids. The plasmids has this nice character of being conjugative. They form these pellets that can connect them to other bacteria that are usually from the same species or from closely related species. These sex pellets, as we call it, one strand of the plasmid break and just go from this bacteria to another. And as it happens, it transfers everything in the plasmid to the other bacteria, and the other, and the other, and the other. So it can and it will be transferred to other bacteria easily, especially in the hospital areas where these organisms are just in very close vicinity. They are just around each other, and they are around the patients who develops easily due to misuse of antibiotics resistant strains. So these plasmids just transfer from one bacteria to another. That's why we call it horizontal. Horizontal, it means from the same population. It's not vertical. Vertical, it means from the mother to her daughters and the offsprings. So the horizontal, it means in the plasmid just use these ducts to transfer itself from one bacteria to another, and from the other bacteria to others, and so on. These transposable genetic elements that are listed after them just jumps from the plasmid to the chromosome, from the chromosome to the plasmid. So it can jump from one bacteria to another as well. The plasmids from very interesting extrachromosomal DNA that transfer resistance. They are responsible for beta-lactamase enzymes that we suffer from nowadays, acetyltransferase enzyme against chloramphenicol, enzyme produced acetylation, adenylation, and phosphorylations of aminoglycosides. So they are responsible for a lot of resistance that we are suffering from these days. Transposable genetic elements are the same. They are responsible for multi-drug resistance all over, in Enterobacteriaceae groups, even in staph and gram-positive bacteria as well. So that's what I'm talking about. These are the plasmids, as we see, by a process called conjugation. It can transfer itself from one bacteria to another. The transduction as well. Transduction is made by a certain phage. What's the phage? It's a bacterial virus that can infect the bacteria, and it can transfer part of each chromosome from one bacteria to another, and the transposable genetic elements that can be transferred through a phage or through a plasmid to other bacteria. And the other process is called transformation. Transformation is just picking up foreign DNA from the surrounding. All these processes, actually, is very rare, very rare. The most common are the conjugation and transduction. Conjugation and transduction mediated usually by plasmids or phages, which are bacterial viruses. So, what are the mechanisms of acquired resistance? What are the mechanisms? The mechanisms of acquired resistance are classified into 5 groups. Reduction of intracellular concentrations of the antibiotics, inactivation of antibiotics, target modification, target elimination by new pathways, and target overproduction. Let's talk about it one by one. Reduction of intracellular concentration of the antibiotic. Just imagine that the bacteria are imagining that these are thieves are coming to take its gold from its home. So they are trying to resist these antibiotics by any way. So they are trying to decrease their concentration in their home. So what are they doing? Decrease the influx. Reduction of the permeability of the purines. To any antibiotic to enter, it must go through certain protein in the cell membrane of the bacteria. These are called purines. The modification of them, decreasing their number, abolishing their number, so the thieves cannot find the door to enter into their home. Okay, so This is one of the mechanisms. Reduction of the uptake or increasing or efflux pumps. Either they don't find the way in by finding their door, they cannot enter by not finding their proteins to enter into the cell, or efflux pumps. Just as the thieves comes, they are thrown from the balcony. So the bacteria are taking them in and then throw them away. So they will never reach a certain concentration that will be effective against the bacteria itself. This is the first mechanism. Never the concentration reaches an effective level through either blocking the door for them, no influx pumps, or increasing their efflux pumps. Inactivation of the antibiotics. So the bacteria knows that that's the enemy, so they are throwing at them hydrolyzing enzymes. Hydrolyzing enzymes, beta-lactamases, hydrolyze all the beta-lactam brings antibiotics, inactivate them as penicillins, cephalosporins, carbapenems, every beta-lactam containing ring antibiotic. Acetyltransferase, still mentioning just shortly, chloramphenicol against chloramphenicol, aminoglycosides, modifying enzymes as well. This is the second mechanism. The third mechanism, by changing their target. So the antibiotic doesn't work except if it finds its own receptor or its own enzyme. So what happens if I change this lock? It cannot work except by key and lock. True? So if I change the lock, what happens? It cannot enter into the cell, or it cannot work on the enzyme it works on. So the resistance against aminoglycosides due to altering proteins on the 30S subunits of the ribosomes works that way. He alters the 30S configuration, so it doesn't work on them. Resistance of macrolides, erythromycin, streptogramins, linezolide, all these are working by the same pathway. Altering penicillin binding proteins as well, changing the shape of the enzyme or the receptor which works upon. Target elimination by doing a new pathway. Sulfonamides and trimethylprim works on the para-aminobenzoic acid, which is a precursor for folic acid, which is needed for DNA production. So sulfonamides and trimethylprim works on this pathway. So what happens if I took ready-made folic acid? So what happens if actually they prevent forming folic acid? It's fine, because I'm taking ready-made folic acid from outside. Target overproduction. Target overproduction, that happens with vancomycin. Vancomycin works on the methylglycan layer in the cell wall of the gram-positive bacteria. So what happens if it breaks it down and I build it faster than it breaks? So I'm overproducing the cell wall as it broken. I built it much faster, and this usually leads to tolerance to vancomycin by time. These are the mechanisms of resistance to antimicrobial agents. Either, as we said, efflux pumps, blocking the way in by changing the target, changing hydrolyzing enzymes, and so on, as we said. So how we fight drug resistance? How we fight? What are the strategies we use to tackle this problem? In hospitals, we have to improve our infection control procedure. Our infection control must be strict, must be followed very strictly. Implementing, enforce policies for prescribing antibiotics. It should be monitored. Actually, should be recorded. Records should be kept everywhere. In the pharmacy, in the microbiology lab, for sensitivities, it should be reported to the pharmacy to know what's the working antibiotics and what's is not working, and the research is done everywhere. So in the hospitals, it should be done every time to see the most important prescribed antibiotics and change to these working antibiotics. Actually do that every 3 months. The infection control team usually it meets, usually they meet, I'm sorry, every 3 months, and they usually follow the procedure and see the records, which antibiotic is working, which is not working. We can change the antibiotic policy. Let us put in mind that there is an empirical treatment used. Are we familiar with the term empirical treatment? Yes? Yeah, empirical treatment. Empirical treatment, it means that we use antibiotics blindly. We don't know if it's working or not. Just on clinical basis, just clinical basis. Is it good? It's not good, but sometimes it's life-saving. We have to do it, especially in the ICU unit. What happens in the ICU that the patient develops, he's immunocompromised patient. He's been there for 2 months or so, maybe, or even more sometimes, on a ventilator. He's developing every day a new infection. So I have to use an umbrella of antibiotics to preserve his life. So I'm not waiting for the lab to tell me what to do. That's right. So what happens is I have to know which drugs to give this poor patient. And what's not working in my hospital, he will die. So we have to keep records, we have to do our work, we have to make researches about the patients and what's working and what's not working, and change the policies of the hospital according to that. And these policies, it should be strict policies. And the pharmacy plays a very important role in this subject. Usually, we use narrow-spectrum antibiotics because the broad-spectrum antibiotics develops resistance. Combined therapy, sometimes, the rule using one drug. This is the rule, and this is the best. But sometimes, especially in the ICU unit, as I said, maybe it's better to use a combined therapy. So if a resistant strain emerges, the other antibiotic overcomes it, or the other, and so they work together to minimize the risk of developing a resistant strain. Monitoring and surveillance for antibiotic resistance pattern, of course, it's a must in every hospital. Vaccines were available. I don't wait till my staff become ill. I just give them vaccines. I'm sorry. So what about the community? Education to doctors and patients. No antibiotics, please, for viral infection. Please don't give antibiotics for viral infection. Vaccines is very helpful among especially in school, in any gatherings. Combined therapy for TB is a must, of course. Limit the use of antibiotics without prescription. Prohibit the use of antibiotics in non-therapeutic purposes, especially in livestock. Please don't use it in farms. Foodborne infections, especially Salmonella and the Campylobacter, it's nowadays everywhere, especially in poultry. Post-processing contamination after industrial form of poultry, especially poultry, again. The same handling, reducing antibiotic use on farms. Other alternatives. Now we are developing new antibiotics by the help of our colleagues in chemistry, synthesis of new chemical entities, screening for new antibiotics. We usually nowadays in the marine life, in fishes, on frogs, in the whales, we are just screening for new species to produce new antibiotics. Peptide antibiotics, such as products of our own natural immune system. They are broad spectrum against gram-positive, gram-negative mycobacterium. They are new and they are potentially going to be very effective against infections. Revitalizing old antibiotics, using the old antibiotics, try them once more and and even use them in combination. Nowadays, they are trying the old antibiotics in combination against MRSA, especially in biofilm formation. You know, biofilm is a big problem right now. That's us trying to find a new antibiotic. So, using prebiotics and probiotics, we are familiar with these terms. Probiotics as using microorganisms in food. You know yogurt? You know there is a microorganism in yogurt? You know that? So we are trying to increase the antimicrobial, the friendly antimicrobial inside our intestine to improve our health. Is it effective? Yes, it's very effective. Yeah. Actually, it's sometimes the only treatment. You know, in the broad spectrum, using broad spectrum antibiotics in the hospitals for a very long time, we developed what's called antibiotic-produced diarrhea. This antibiotic-produced diarrhea, the only treatment for it is stopping the drug, the broad spectrum antibiotic, and using these friendly organisms. What about prebiotics? Prebiotics are the food that increases the probiotics. Just like garlic, tofu, onion, a lot actually of food are very effective in enriching and increasing our probiotics. What about bacteriophages? Bacteriophages are viruses that can infect bacteria. Can we use them as a treatment? Yeah, actually. There is a lot of research regarding that, especially in Campylobacter and Salmonella, as well as TB, tuberculosis. There is research all over the world around this subject. So natural products, of course, natural herbs, natural products, green tea, tea trees, and eucalyptus, eucalyptus oils. So these are new methods for alternative uses of antibiotics, just to decrease this use of antibiotics. This is our friend bacteriophage. Including to a molecular pathways, preventing the DNA of the bacteria. Using an antisense agents, these are complementary DNA that binds with the DNA of the pathogen to prevent the virulence agents. The antisense agents are either DNA or RNA to prevent the transcription of the messenger RNA. Pharmacyclubksu is a treatment for cytomegalovirus retinitis. It's FDA approved. Other alternative as well are small or short interfering RNA. They are complementary RNA that binds messenger RNA and degrades it. And it inhibits translation, not transcription, but translation as well. So we talked together today on the general mechanisms of acquisition of antibiotic resistance, chromosomal mutation, acquisition of resistance plasmids, acquisition of modification of genes by horizontal transfer, as well as lacking the target itself by natural or inherent resistance. The mechanisms of resistance via destroying the antibiotic molecules through certain enzymes, making it less permeable, altering the target molecule, actively bumping out the antibiotic, and alternative targets for antibiotics as folic acid, taking it ready-made from the environment. These are some useful, interesting websites if you are interested in this subject. Ouch.